Thank you.
Rus, welcome.
Thank you.
We are grateful for your time. And on the stage, on the screen, Ruslan Salakhutdinov, recent advances in deep learning. Please, welcome.
Great, thank you everybody. Can you see my slides?
Yes.
Oh, okay, excellent. So I'm going to be speaking in English, but I guess whenever you have questions, you can ask questions in either English or Russian, if you'd like. Okay, so I'll dive right into this. So my name is Ruslan Salakhutdinov. I am a faculty in the machine learning department here at Carnegie Mellon University. I'm dialing in from Pittsburgh. Sorry, I couldn't be there in person. And I'm also working as a director of AI research at Apple. But today I'm going to talk about some of my work that I'm doing with my students at CMU. So you've probably heard that the impact of deep learning over the last few years is pretty staggering, right? If you look at speech recognition, if you look at computer vision, recommender systems. Even in places like language understanding, which I'll spend a fair amount of time talking about, as well as in places like drug discovery and medical imaging analysis. But ultimately, what we want to do, or what we do, is to develop algorithms that can, that can display human-like intelligence, that can see and recognize objects around us, that can understand human speech, that can reason in language. And I'm going to show you some examples of using reinforcement learning algorithms to develop agents that can navigate and explore, that can plan. Now, what I'd like to do in this talk is I'd like to show you some of the key challenges. And these are the areas in the deep learning community that a lot of us are working towards. So one very important area of research is multimodal learning. And you can think of multimodal learning, I'm going to show some examples, as combining different modalities like images and text, speech, sound, and video, right? So anytime you're dealing with different sorts of data, how do you combine it into representations? Out of it, we're going to see some examples of reasoning, attention, and memory. So how do we get our systems to reason? Store important information about the past so you can act optimally in the future. Natural language understanding is another big area of research, and I think there's a lot of work that needs to be done in that space, in particular getting our systems to reason and understand human language. And also, recently, in the last few years, we've been seeing really amazing advances in deep reinforcement learning. And I'm going to show you some of that work as well. So let me just show you a few examples. 4 years ago, one of my students was working on caption generation. And we started looking at neural networks for processing images as well as generating sentences, describing what's going on in the images. So here you're seeing some examples. And back in 2014, we actually thought it was pretty amazing. If you look at 10 years ago, people in the computer vision community wouldn't believe that you could do things like this. Like, for example, here you're saying, there's a cat sitting on a shelf, or a little boy with a bunch of friends on the street. But, you also sometimes have these examples. A man is holding an apple in his mouth, or two men are playing frisbee in a park area. And the reason why this is happening is because, existing algorithms cannot deal with samples that are outside of its kind of training distribution. So these models were never trained on images of sports images, right? And so that's why it's making these mistakes. There's another pretty exciting area of research where you're doing understanding images. In this case, you're doing caption generation, but you're also using visual attention. And so visual attention, it's here, for example, when you have a system generating a man riding a horse in a field, whenever you're generating a man, you tend to focus on the man. Riding a horse, you tend to focus on the horse's head. In the field, you focus on the field. So you can think of these systems as a differentiable attention mechanism that allows you to pay to different parts of the input when you're generating a caption, for example. And we'll see a lot of some examples of using attention in language understanding, in visual question answering, and such. So, and translation systems. So that's a pretty important concept. So how do these systems work? Well, at the high level, it's basically you have a convolutional neural network that extracts features, representations of images, and then you have a recurrent neural network with an attention mechanism. And you can think of attention mechanism as just basically attending to different parts of the input. So you sort of have this sequential process that generates a sequence of words while also paying attention to different parts of the image whenever you're generating these words. And again, we'll see a little bit more math behind these models as we go through the talk. Now, let me jump into sort of what I think is one of probably the most challenging areas within machine learning and deep learning community right now. It sort of comes to the problem of reasoning and natural language understanding. So let me show you one example. There's a nice data set that was collected by folks at Chicago, which is a who did what data set. So imagine that I give you some context. These are news stories coming from, I believe from CNN news articles. And let's say I give you an article like this. Arrested Illinois Governor Rod Blagojevich and his chief of staff John Harris on corruption charges and so forth. I don't know if you remember back in 2008 in the US, there was this guy Rod Blagojevich who was trying to sell Obama's Senate seat. So Obama was a senator in Chicago, and Rod Blagojevich was also a senator in Chicago, and he was doing something to kind of try to sell basically his seat to the next senator. And imagine now I give you a query. A query basically says, President-elect Barack Obama said on Tuesday he was not aware of alleged corruption by X, who was arrested on charges and so forth. So the question is, who is X, right? And you can see that these are, pretty difficult data sets. Obviously, the answer is Rod Blagojevich, but the answer could be, Barack Obama. The answer could be John Harris, and there are a bunch of names that are mentioned in the context. And the query itself, you have to understand the query in order to be able to answer that question, right? And so it's a fairly challenging data set. People are pretty good at doing that. Machines are not so good at doing that. Now, at the heart of all of these models, particularly models that are based on understanding text or any sequential data, videos, for example, as well, at the heart you have these so-called recurrent neural networks. And there are various flavors of recurrent neural networks. The most popular ones are, models that sometimes called LSTMs, long-term short-term memory networks. So these are different variations of RNNs. But the basic idea behind recurrent neural networks is the following, which is kind of summarized in this equation, which is you have some hidden state at the previous time step, right? So think of it as a hidden state as a summary statistics of everything that happened up to t-1. You have a matrix U, which is the parameters you multiplied by the state. And then you have input at time t. So you think of it as, the observation that's coming right now. So that could, for example, be a word at a specific position, right? So you're adding both of them together. So you're adding the previous hidden state. You combining it with the current input. And then you're passing it through nonlinearity. And these nonlinearity could be sigmoid nonlinearity, 10H nonlinearity, or any other nonlinearities. If this nonlinearity is a linear, so think of it as just a linear function, then you're essentially going to be recovering traditional models like linear dynamical systems. And under certain conditions, you can recover models such as hidden Markov models, for example, right? So you can think of recurrent neural networks as nonlinear extensions of your traditional linear dynamical systems, Kalman filters, and so forth. And one of the things that I want to point out here is that we've been looking at models that instead of doing this additive integration, right, of combining hidden states and what you're observing right now, we were looking at multiplicative integration. So here you're basically doing element-wise product between the state and the observation. So you can think of it a little bit as a gating mechanism, right? Because if the input is 0, then you're basically saying, there's nothing that's important for the hidden state. And so the observations or the hidden states, they can gate each other, right? Because here you're doing element-wise multiplication. And you can look at the NIPS paper, basically, there are some very nice properties with this gating mechanism that allows you to build models that I think are much more stable and also give you much sparser representation. So it's much easier to optimize these models. And you can do it in the context of long-term short-term memory networks, LSTMs, and various flavors of recurrent neural networks. And so what we've been doing here is we've been basically using recurrent neural networks to encode document and the query. And this is done for different models. And here we're using what's called gated attention mechanism, which is essentially, again, is an element-wise multiplication between the words that are coming from the query, from the question, and the words that you're seeing in a document, right? So this element-wise multiplication gives you nicer representation, sparser representation, also gives us far better prediction accuracy. Right? But in hindsight, what's happening with these models is that you have a query, you have a document, and you're basically using this gating mechanism to figure out which words in the query are more similar to the words in a document. So you can pick up relevant information that's relevant to the query from the document. And what's important about these models is that you have so-called multi-layer representation. So you have multiple levels of extraction of structure from the documents, and you're probably familiar with things like convolutional neural networks. So you can think of these models as, maybe like a souped-up version of convolutional networks, except for every single layer is now recurrent, bidirectional recurrent neural network. And more recently, there's been a lot of work, actually in the last year, where you're replacing these recurrent neural networks with something that's called transformers. And you can use different ways of encoding information without actually relying on recurrent networks, but doing something similar to that. And now you pass this information through multiple levels of representation at the end of, and then you basically try to predict the correct answer. Right, so these systems, I just wanted to show you that these systems are now becoming far more complex, compared to traditional architectures. One interesting thing that comes up from these models is because we're doing this gating mechanism, we could basically look at attention. We can look, for example, in this example, in the first layer, if we look at alleged corruption, the context around alleged corruption, it has high attention with Rob Blagojevich and Governor Rob Blagojevich. So which basically means that this particular attention picks up the relevant information from the document. And then second layer, you basically associate Senate sit with Rob Blagojevich. So what's happening with these models is that they seem to be able to discover these meaningful features like Senate seat and alleged corruption, which is important for making accurate predictions, right, to answer this query correctly. And so instead of you specifying by hand what are the right features or attributes in the text that you need to pick up and pay attention to, these models are able to do it on their own, right? Because you're basically saying, pick up me information in such a way that I can predict the answers correctly, which is pretty interesting. One of the things that I think that we've been working in my lab and a lot of folks in the research communities is how do we incorporate prior knowledge? How do we design new architectures for neural networks? So how do we, maybe we can look at dependency parsers, maybe we can look at entity relations, word relations, or maybe we can look at designing new architectures for recurrent neural networks in such a way that we can design better priors so that we can have better representation of our textual data. And I wanted to show you one thing where we've been trying to do it using so-called explicit memory. But let me show you what I mean by that. Imagine that I give you 3 sentences. Mary got the football, she went to the kitchen, she left the ball there. And then imagine I ask you the question, where is the football? Or where's the ball? And obviously the ball is in the kitchen, right? But it's quite difficult for machines to kind of propagate this information forward, right? You have to understand that Mary has the ball and Mary went to the kitchen and now she left the ball in the kitchen, so the ball is in the kitchen, right? So for us as humans, it's pretty trivial. For machines, it's pretty difficult. But what we can do, we can use sort of what's called coreferences. We can associate Mary and she, that means the same thing. Or we can use synonyms like football and ball, that also means the same thing. So we can introduce these extra links or these extra information into textual representation. And then there is a way of doing it efficiently, or what we call graph coding. So we're constructing a graph and introducing these additional links. And then there is a nice way of integrating that information into recurrent neural networks. So the overall structure still remains the same as a recurrent neural network. And that tends to give us much better results because it allows us to propagate information at much larger scales, right? Obviously, provided that our core references are correct. Let me now jump into even more difficult domain. This is something that I'm, becoming much more excited about. This is the work that we've done in the last year, finding answers to factual questions when you ask these questions in natural language. And obviously, you think about personal assistants or, you communicating with, your home devices. You want to be able to ask any questions and get the right answers, right? So for example, you can ask the question, who voiced Meg in Family Guy? So Family Guy is a show in the US and Meg is a character in that show. It's like a cartoon. And the answer would be Lacey Chabert and Mila Kunis. So both of them were voicing Meg in a Family Guy. But then if I ask you the question, who first voiced Meg in a Family Guy? You want to be able to answer that it's Lacey Chabert, right? And so how do we get that information? How do we find this information? Well, it turns out that a lot of existing systems today, if you look at the big companies like Google and pretty much anyone that does search and try to find these answers to these questions, a lot of it is people are relying on knowledge bases, right? So the idea here is that you have a big knowledge base of, people's names, their relationship, who stars in what movie and what not. And it's, you have these gigantic knowledge bases that you construct. And now if I ask you who first voiced Meg in Family Guy, you have to do what's called semantic parsing. You have to identify these entities and you have to figure out how they related to the entities in the knowledge base. But once you construct this query graph, once you find the right information in the knowledge base, then the answer is pretty easy, right? Providing the answer is pretty easy. The issue with a lot of these systems today is semantic parsing is extremely difficult to do. It's an extremely noisy process. Sometimes when you talk to your personal assistant, sometimes you feel like, why isn't my personal assistant get what I'm saying? And in many cases, or why am I searching for something and I don't get the right information back? In many cases, it's because the semantic parsing is failing, right? Finding that Meg actually corresponds to Meg Griffin, and the Family Guy is a specific show versus you talking about something else. That's a difficult task. In the last few years, people started shifting more towards using unstructured text as a knowledge source. So you can think of it as you go to Wikipedia, you use recurrent neural networks with gated attention mechanisms to try to find the answers, right? So you do information retrieval, and then you do reading comprehension, so finding information by reading lots and lots of documents. And these models have been becoming more and more dominant in the last few years, right? So they're a little bit more expensive, but you can find, sometimes they're more accurate than using the knowledge base. But what we've been trying to do, we've been trying to develop a system that basically combines information from the knowledge base with information that's coming from unstructured data, like Wikipedia, for example, or just web pages on the web. And there is a way to propagate information between these two different sources. One is a graph-based propagation. The other one is more like a recurrent neural network-based propagation. So, and how do we read graphs? Well, the idea of reading the graph is the following. Let's say we have a graph. We have vertices, which represent our entities, names, and we have edges representing relationships between those entities. We have a natural language question queue, and our goal is to learn a function such that this function takes value 1 if it's a correct answer, or 0 otherwise, right? And we want to be able to build a model given a knowledge graph where we basically say probability of the correct answer is given by the softmax of HQ and HV, where HQ are the questions that are represented by using recurrent neural networks, so different flavors of recurrent neural networks, and HV is the not representation that we get from using graph convolution. So it's a way of propagating information on the graph. So it's interesting, in this particular representation, you're both using recurrent neural networks, but you're also using graph convolutions. And the graph convolution network is actually, it's a pretty simple concept. You're basically recursing on the graph, right? So instead of, in your traditional recurrent neural networks, it's a time series, so you recurse according to the time series. Here you're recursing according to the graph, right? You're basically looking at nearby nodes, you aggregate information, and you propagate that information to the next node. There has also been a lot of interesting work on relational graph convolution, right? It's fairly recent work, where you basically have graph with H types. And so these H types could correspond to different relations. Right, and so different relations meaning that, maybe someone was born somewhere, or someone was working somewhere, or someone was an actor in that movie. And so these would correspond to different relations. And you propagate information according to different relations, right? So different edges would represent different relations. And so in our case, we've been looking at representing entities using, your traditional word back representations. Documents were represented using recurrent neural networks, LSTMs, and then the information can flow from entities to the unstructured data, to the documents, using recurrent neural networks, right? So here you can think of it as kind of like doing reading comprehension task. On the other hand, we can also take information from the textual data. Think of taking information from Wikipedia, for example, and forcing it to find better representations in our knowledge graph. So the information can flow from documents to the knowledge graph as well. So to me, that's exciting because now we have these two very different sources of data, and we can propagate information between these two sources of data. And you should, we have a paper that describes the mathematics behind it. We have code, data set, so you're more than welcome to basically reproduce all the results that we have in the paper. And it's, we do see some substantial improvements over, either just using knowledge graph, which is typically noisy, or semantic parsing is hard to get, versus just using unstructured data, you doing your standard reading comprehension task. So combining both gives us these hybrid models, give us much better representation. And then, I also want to point out that we've been looking at systems that go beyond just simple question answering, but systems that basically have to do a little bit more reasoning. Reasoning by aggregating information across multiple documents. So here's, for example, one example of the data set, and again, it's also available online, and the code for basic models is available online, but it's a pretty challenging task. So here, for example, you have one particular document that talks about a particular tugboat, which is a historic tugboat. It's located in a particular town, waterfront in Sarasota County in New York, and it describes about this particular tugboat, right, which you can think of it as like a historic piece of work located in that city. And then there's another paragraph that basically describes the city. Waterfront is a town in New York and its population, so it just talks about, about the town. Now I give you a question, and the question says, what was the population of the town where the historic tugboat is located? Right? So I'm basically asking you, what's the population of the town where this particular historic tugboat is located, right? So the interesting thing about this is that you cannot answer this question by just looking at paragraph A or paragraph B, right? You have to look at both of the paragraphs, and you have to make certain inferences. You have to understand that tugboat is located in waterfront, and the waterfront is a city or is a town, and then you have to connect it to basically saying, oh, waterfront is a town that has that many people living in it, right? And then you can answer the question. And so this is sort of much more difficult, right? Because now you have to find the relevant information, and then you have to make inferences about what is it, how do you answer the question, right? And so you have to understand that there is this waterfront, Waterford, which is a town, which is important. And so, another example that I typically like to give is that if you go on Google and you type in where was Facebook born, right? Or where was Facebook originally started? And you can't answer that question because nowhere on the web it says Facebook was started at Harvard by Zuckerberg, right? But you have a bunch of information that says Facebook is a company headed by Zuckerberg, and then you have a bunch of things that basically Zuckerberg was a student at Harvard. But you cannot answer the only way to answer this question if you have much more intelligent algorithms that can aggregate information across these different sources and make right inferences, right? So here we're trying to basically make a little step towards building algorithms that can reason, that can pay attention to the relevant pieces and be able to reason, right? So that you can provide better answers, right? Which is a lot of systems today don't do that. Okay, so in the last part of the talk, what I'd like to spend a little bit of time is also talk to you about reinforcement learning, deep reinforcement learning. That's another area that we've been seeing a lot of success and a lot of excitement, even though this area has been around for a very long time. So what is deep reinforcement learning? Reinforcement learning. So reinforcement learning in particular, it's about learning behaviors. It's about mapping sequences of observations to actions to achieve a particular goal. Right, so you can think of it as observation that's coming in. Think about you're trying to fly a drone. The observations are a sequence of frames that are coming in, and the actions are turn left, turn right, so in robotics, it's pretty straightforward what those actions should be. But it's interesting also that even in the space of dialogue-based systems and language, when you're having conversation with a chatbot. Many cases, most sophisticated systems are using reinforcement learning, where the action is to basically either follow up with a question or choose what kind of answer, choose what kind of question a chatbot should be asking, right? So reinforcement learning, I know in the space of financial markets, sometimes people use reinforcement learning where your agent takes a particular action, like executing a particular order, buy or sell a stock, for example. So it has a very diverse set of applications. Now, reinforcement learning itself, is the basic formulation of reinforcement learning is the following. Imagine that you have an algorithm, you have an agent. The agent takes an action. Buy a stock, turn left, increase your velocity, or whatever those actions might be. And then the environment gives you back a new state, right? And then given this new state, you take another action. Right, so it's always in the sense of you take an action, you get the new observation. You take another action, you get the new observation. And then sometimes the environment gives you rewards. And you can think of these rewards as positive rewards or negative rewards that tell you something about your behavior, right? And the goal is to kind of reinforce with positive rewards good behaviors. Right, and typically, you have a robot and you try to get it to walk around. You could say, well, if the robot goes through the door, you give it positive reward. If the robot doesn't reach the door, you give it a negative reward, right? And so teaching the robot to kind of navigate around. And reinforcement learning produces policies, right? You can think of these as policies that, again, map observations to actions. And the goal is to maximize long-term reward. And so there's a mathematical formulation behind reinforcement learning. I'm not going to get too much into that. But in the last few years, you've probably heard about deep reinforcement learning. And the only difference from reinforcement learning is that essentially you have a parametric function, which is a deep neural network function that maps observations to actions. Right, and again, observations could be high dimensional, it could be images, it could be video, sound, any multimodal input that's coming into your agent. And your output is just basically a sequence of actions. Could be continuous actions, like change my velocity, orientation, or could be discrete actions, such as turn left, turn right, buy a stock, for example. And you're updating parameters to maximize overall reward function. And there's lots of different algorithms. Something that's called Q-learning, actor-critic, evolutionary strategies. There's a, you can basically teach the whole class on reinforcement learning. Now, what I'd like to emphasize here is that in the last few years, in my view, one of the biggest advances in reinforcement learning and in deep learning in particular is this notion of learning external memory. There's a wonderful work that's coming from my colleague Alex Graves at DeepMind, who was, it's kind of like when I was a PhD student, he was a postdoc in Jeff Hinton's lab, so we were hanging out in the same place. But he basically developed this notion of external memory, which is a beautiful work. I encourage you to look at that. It's basically a way of defining new architectures with differentiable writing and reading operations, which is pretty cool. It basically allows you to have these differentiable mechanisms, and that allows you to store information and retrieve information. And you can do it in a differentiable way that basically means you can train these systems using, gradient descent algorithms. But before I get into having external memory, let me just show you how deep reinforcement learning can be used for learning to play a three-dimensional game. So here's what you're basically trying to learn to navigate. So what's the input here? The input here are the frames, what you're observing on the screen, which is a bunch of pixels. And the output are the actions: turn left, turn right, move forward. And the reward function here is basically collecting objects. Try to collect as many objects as possible. So what's remarkable about this is that you're not teaching the system to say, oh, here's how you navigate. You're basically telling the system, figure out whatever you need to do such that you should collect as many objects as possible. Right? And just by collecting objects, it's learning to navigate in this environment. And it's through the process of learning, it doesn't get stuck at the corners, it doesn't go to the lava, and so forth. And you can train with random textures, navigating in these environments. And then what's interesting is that if I place you in a completely new environment, the environment that you've never seen before, you have no problem navigating in this new environment, right? Which is, you can generalize fairly efficiently. And now I throw you an unknown map and it's no problem. You move around, you don't get stuck, and so forth. The other interesting thing about this particular formulation is that there was a contest of playing Doom game between different reinforcement learning agents, and it turns out that these agents can outperform human players, right, in terms of playing like a first-person shooters game, which is pretty interesting. But the problem with these models is that they are very reactive. There is no notion of memory. You're just moving around, you see someone, you basically shoot, or you just trying to just kind of like randomly moving around. There is no notion of memory, there is no notion of strategy, there is no notion of planning. So we've been looking at trying to learn a structured memory so that we can remember something about the past so that we can execute optimal actions in the future. Let me give you a little bit of motivation. Why this is a problem. We all know that learning long-term dependencies is an extremely difficult task, in machine learning in particular. So imagine that I show you this random maze. It's kind of like what you're seeing in Doom. And there is something called indicator. And the indicator could be blue or green. If the indicator is blue, you have to find cyan block. If the indicator is green, you have to find a red block. And these are random mazes. So the agent's never seen that maze before, right? So why is this difficult? If I give you these rules, if I tell you, if you see this thing, go here. If you see this thing, go there. Then it's an easy problem. But imagine that I throw you in the maze and I don't tell you anything about these rules, right? And what happens is that the agent moves around, sees a green block, goes to the red state, gets some positive reward. And it says, well, every time I hit the red state, I get positive reward. So next time I go to the red state. Next time you go to the red state, you see negative reward. Now you're saying, what's going on? Sometimes it's positive, sometimes it's negative. And through the process of learning, you have to figure out that there's another something in the environment that's actually indicating to you which target you should be navigating towards. And now the problem is that the time that it takes you from observing the state of the indicator to finding where you need to go could be arbitrarily large, right? And it's extremely difficult for even recurrent neural networks like LSTMs and such to do that. And so we've been basically looking at what we call neural map, which is a writable memory with a specific inductive bias. What we do is we assume that we know the location of the agent. And if the agent in a particular location, we store information in the map, what we call a memory map. In a different location, you store it in the memory map. In a different other location, you store it in another map. And so the question now becomes, how do you learn what you need to store? How do you learn what you need to read from the memory so that you can take optimal actions going forward, right? And the way that the system works is that you get an observation, you extract features from what you're observing, and then you write it into the memory. And there's a specific way of doing it, it's a differentiable way of doing that, and then you take an action. The action, turn left, for example. At the next time step, you read from the memory, and you have to learn what is it that you need to read from the memory, such a way that you can update the memory and then take the action, and so forth. Right? And so you have this persistent structured memory that persists over time, and you're kind of writing to it and reading from it in a very specific way that allows you to learn to store important information about the past. And so if you look at the neural map operations, I don't have time to go through the mathematics of it, but there are so-called read operations, and these are differentiable operations that basically look at how do you read information from the map. There is a sparse write operation at the agent position, which basically means that whatever you observe and whatever you have a context of your map, you write it into the memory. And again, that can be done in a differentiable way, so you can backpropagate gradients through these operations. Then there is an update step, which updates the contents of the map. So as you explore the environment, you can write more into the memory. And then there is a policy. Once you have your state, your observations, what you have in the memory, then you basically have a policy that basically maps steps to the actions, right? Taking memory into account. And so here's an example of an agent navigating in the environment. It's a completely random maze. You've never seen that maze before. It navigates, it goes to the wrong target, it sees that it's the wrong target, it backtracks, and it explores the maze until it finds the right target. So this is completely learned from the data, right? So it actually learned that there is an indicator, and I need to remember the state of the indicator, so it writes the appropriate information into the memory and eventually reaches the right target. Right, so everything is learned. These causal rules are being learned by just running lots of simulations and having this map to remember, neural map to remember what's going on. And then even going beyond that, we've been looking at the systems where we can say, well, fine, we can have memory. We've talked a lot about language understanding. How about combining both? So we have a bunch of projects which basically have the following flavor, which is, can we train our agents to follow instructions? So for example, the training time, you say, go to the short red torch. And the reward function is, if you hit the target, you get positive reward. If you don't hit the target, if you go to the wrong place, you get negative reward, right? So you sort of have to go through the process of figuring out what these instructions mean. And that's why sometimes it's called language grounding, because you basically have a meaning of the word logic, for example, or green, or torch. And so, this is what happens with these agents, is that you take a language, you process using LSTM. In fact, the model itself is basically, it's almost like a gated mechanism, gated attention mechanism. And then it has to learn to explore as well, right? It has to move in the environment and figure out what it means. So for example, it figures out what's the meaning of the short blue object or the tall red object. Because in many cases, understanding the meaning of the word tall or short or smallest is quite difficult, right? Because it's a relative concept. But through the process of training, eventually, it's actually learning to move around and figures out what the largest, what the smallest mean, and kind of generalizes to new objects and generalizes to new instructions, which is pretty remarkable. It's a very first step, so it's the environments that we're working right now are quite limited. But we're trying to extend it to the systems that can deal with, hundreds of thousands of different instructions and understanding the language behind it. Now, the other one last thing that I want to point out is this notion of navigation, which is known as simultaneous localization and mapping, or SLAM. And the idea is It's a very old concept from robotics communities where you're basically trying to navigate in the environment and understand where you are, and also construct the map of the environment. So in this particular example, this is what we call active neural localization, where I throw you in the environment, and your belief map is telling you your belief where you might be, right? And you can see the belief updates based on the actions that you're taking. So it's a combination of kind of reinforcement learning, as well as traditional approaches like localization and SLAM. And we've particularly been looking at end-to-end learning of SLAM by basically replacing a lot of existing SLAM algorithms, which are not very robust and not very accurate with sort of neural network style architectures, with attention, with plus reinforcement learning to sort of solve these problems and be able to solve these problems much more accurately, faster, and so that we can also deal with different variations in the environment as well. So on that note, let me just summarize and say that ultimately what I'd like to do is to build agents that can navigate autonomously, agents that can localize in the environment, agents that can plan, agents that can have memory, right? Dealing with multimodal inputs. We've seen a little bit of that, combining language, speech, sound, understand human speech, maybe instead of just providing natural language instructions, providing instructions by voice. Reasoning and natural language understanding, I think that's an important area of research, and I've shown you some data sets and some approaches, but we're very far from building systems that can, that can aggregate information and actually reason it, instead of just providing, simple factual answers. And recognize objects around us, and how can we do it in sort of one framework as one agent. So these are all pretty exciting areas of research. So on that note, I'd like to thank you so that I'm not running out of time. And I think we have a few minutes for questions. So thank you.
Ruslan, thank you. It was really motivation and interesting topic. Can you tell a few words about award approach what you use to award for something your system? I mean, it can be different tasks, go through the shortest way, or kill all enemies, or collect all stuff, or something like this. How you award it?
Yeah, so that's a very good question. I think that so one of my students, I mean, he wasn't my student when he was doing this work, but he was basically in the case of Doom environment, for example. You can think of it as you're basically training a system that can play, for example, a first-person shooters game, and you have teams that are playing with each other. The reward function that you're training against is basically collecting as many objects as possible, not dying in the environment, and also, killing other aliens, right? Like there are a bunch of aliens that move around in Doom environment, and you have to kill as many aliens as possible, right? And so, so this is something, and the behavior that the agent is learning is through the process of trying to maximize its reward, trying to maximize, the number of objects that you're collecting, maximize the number of aliens that you're killing, and such. And, from when we started working on this problem, one of my students was working on a problem and was kind of looking at an example of Doom or Quake. And what was interesting is that, you kind of, these agents would learn behaviors that humans might not do, right? So for example, in a game of Quake, my student was kind of like trying to play the game of Quake and try to build an agent that can play Quake. And it was interesting because initially the agent, during the first stages of learning, the agent would just randomly shoot around. Because accidentally you'll shoot someone, you get positive reward. But then someone shoots you and you die and you get negative reward. And through the process of learning, then the agent would basically do something like it, go to the corner and sit in the corner and just kind of like shoot aliens that are passing by, right? So that's another behavior that it eventually learned. And then after a while, it learned that actually I'd better move around because I can, shoot as many more elements, and I can get much more reward. So it's very interesting that you sort of go through this process of learning different policies, and the only goal is so how do you define the reward, right? A lot of work in reinforcement learning is basically reward shaping. How do you define the reward so you can learn these optimal or these accurate policies, right? And if you think about, there's been some examples of people at OpenAI, playing Dota or playing StarCraft, which is much more sophisticated environments, or the game of Go. In many cases, it's just, it's reinforcement learning combined with multi-colored research. You do a little bit of planning, combined with deep learning, and it's, and ultimately you sort of try to figure out what the right reward structure you should be using.
Hello.
Yes.
Thank you for your talk. Really inspiring. And you mentioned in one of your talks with Andrew and G that challenges of unsupervised learning are inspiring you and you want to work with. Are you working on one of such challenges now, or the main focus is on reinforcement learning?
Yeah, so that's a very good question. So one of the challenges, I agree. So I generally say one of the challenges is unsupervised learning. And I still believe that unsupervised learning is a really important challenge. We are working on unsupervised learning. Particularly, we're looking at generative models, deep generative models, trying to build interesting distributions over the input space. But one of the things that I think right now is that if I look at unsupervised learning or reinforcement learning, I'm a bit better compared to unsupervised learning. The reason why is you can think about reinforcement learning is there are two advantages. One is that you are interacting with the environment. In many cases, for example, supervised learning of some data, you typically can't interact with the environment, right? Whereas in the reinforcement learning domain, in the environment, you can actually, if you want to learn something about a cup, you can actually come and pick up the cup or move around and see the cup from different viewpoints and such, right? So that's why it's much, it's still kind of unsupervised because you see this new object, you don't know what it is, but you can explore it, right? And the second thing is that in the reinforcement learning, you get these weak signals. So it's not supervised, but you get these weak signals that basically say once in a while, that was a good behavior, or that was a bad behavior, right? So, so I think that's kind of like, I kind of like view supervised learning is something that we know how to solve, right? A lot of success, most of the success in deep learning just comes from supervised learning. Mapping inputs to the outputs, you have enough data, you can do that. Unsupervised learning, there's a lot of work, but we haven't really kind of developed the right algorithms, I think. That unsupervised learning still doesn't work. And then in between, you have this reinforcement learning, right? You're interacting with the environment, but you get these weak signals so that you have better hope of learning about the environment, right? So for example, like I've shown you some instructions, go to the white torch or go to the red torch, right? We never tell the system, this is torch, or this is key, or this is another object. The system, by executing instructions and exploring, it's kind of figuring out that this is a torch and this is a key and such. So it does it in kind of unsupervised fashion because we never say this is it, like for detection. We don't give it a 2D bounding box of this is a torch. So it's to some extent, and it's succeeding in doing it. So we're building these models, and if you actually take part of a model and you can try to use it to detect torches, it can detect torches, right? So which is, in my view, which is exciting. But I still think that unsupervised learning is a really exciting area of research. We just haven't had big breakthroughs or big successes in that domain.
Okay, thank you.
And the last one.
Oh, thank you.
Yes.
Can you please explain a little more about neural map? Is it just like extension to recurrent networks, but something instead of gates you have this writes, reads, and so on, but in concept it's same, or this is some conceptually new?
Very good question. I think at the high level, it's very similar to recurrent neural networks. Similar in the sense that you have this persistent propagation of this two-dimensional structure, which is your map. So you can think of it, you can also think of it as an LSTM model, but with a very specific